Let's look at orthogonal sets. A set of vectors is an orthogonal set if each pair of distinct vectors is orthogonal. For example, confirm that the set 3, 1, 1, negative 1, 2, 1, negative 1, negative 4, 7 is an orthogonal set. Well, let's look at these vectors in pairs. The dot product of the first two vectors is 0, therefore they're orthogonal. In the same way, the dot product of the first and the third and the second and the third, those are also going to be 0. So every pair of vectors is going to be orthogonal. It turns out that an orthogonal set of vectors is linearly independent. I could prove this. You can probably prove it on your own. I'm not going to prove it here, though. An orthogonal basis, you can probably guess what this is going to be, is a basis that is an orthogonal set of vectors. For example, the set S that we looked at a moment ago is an orthogonal basis for R3. How do we know? It's an orthogonal set. We just saw that a moment ago. And it's a basis. How do we know it's a basis? Well, it's linearly independent. We just saw that a moment ago, right? Linearly independent. An orthogonal set of vectors is linearly independent. And any linearly independent set of 3 vectors in R3 spans R3. Now, if you're still not convinced it's a basis, there's another way you can see this. Okay, think about the invertible matrix theorem. If you have a 3 by 3 matrix where the 3 columns are linearly independent, then those 3 columns must form a basis for R3. That's from the invertible matrix theorem, that monster theorem we saw that has many statements. Okay, so this set is an orthogonal basis for R3. Can you think of another orthogonal basis for R3? The set 1, 0, 0, 0, 1, 0, 0, 0, 1 is also an orthogonal basis for R3. Because again, it's a basis, and pairwise, these vectors are going to be orthogonal to each other. We can express vectors in terms of this orthogonal basis. Let V be Rn, or a subspace of Rn, with orthogonal basis V1, V2, dot, 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 V sub k. For any vector y in V, y equals, oh my goodness, look at this hairy formula. It's going to be y dot v1 over the length of v1 squared times v1 plus y dot v2 over length of v2 squared times v2 plus blah, 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 plus y dot v sub k over length of v sub k squared times v sub k. Where does this formula come from? Well, we saw in Calculus 3 that this first term here, do not disturb on, thanks for the reminder. We saw that this first term here is the projection of y along v1. Okay? In the same way, this is the projection of y along v2. This is the projection of y along v sub k. Here's what we mean by this. If you have this vector is v1, this vector is y, the projection of y along v1 is just going to be this. It's basically the vector that you get if you drop a perpendicular from the head of y to v1. It's this vector here, from the tail of y to that place where y intersects, where you drop the perpendicular. Okay, let y equal 8, 4, 7. Express y in terms of the orthogonal basis that we saw earlier. So it's going to be y equals y dot v1 over length of v1 squared times v sub 1 plus blah, blah, blah. So it's 847 dot 311, that's y dot v1, all over length of 311 squared. Length of 311 squared is going to be the square root of 3 squared plus 1 squared plus 1 squared, all squared, so that's just going to be 11 times 311. Plus 847 dot negative 121 over 6 times negative 121 plus 847 dot negative 1 negative 47 all over 66 times negative 1 negative 4 7. Okay, so this is what we saw in the previous slide over here. That simplifies to y equals 35 elevenths times 311 plus 7 6 times negative 1 2 1 plus 25 66 times negative 1 negative 4 7. So we can express y, any vector really, but in this case y, in terms of that orthogonal basis. Note that the denominator, again, it's going to be length of v1 squared. It's not simply v1, etc. And it's not simply length of v1. Suppose we have two vectors, y and u and rn. We want to express y in terms of u and a vector perpendicular to u. Why would we want to do that? We will use this later in the Graham-Schmidt process, which speeds calculations. This is what it looks like in R2. So you've got y in terms of u, so you're going to have just a portion of u, and then a vector that's orthogonal to view. So something like this. Okay, so y is going to equal y hat plus z. Y hat is what we just saw a moment ago. It's the projection of y along u. So the projection of y along u is going to be a multiple of u. Let's say some alpha times u. And z is some vector that's orthogonal to u, perpendicular to u. Okay, we call y the orthogonal projection of y onto u, or simply the projection of y onto u. We saw that formula earlier. It's going to be y dot u over the length of u squared times u. And we call z the component of y orthogonal to u. Z is just going to be y minus y bar. Because if you think about it, y bar, not y bar, but y hat plus z is going to be y. So that means that z is going to be y minus y hat. For example, let y equal 2, 8 and u equal 1, 2. Express y in terms of vector y hat parallel to u and a vector z perpendicular to u. So y hat we've seen before as y dot u over length of u squared times u. It's going to be 2, 8 dot 1, 2. That's y dot u over length of u squared. That's length of 1, 2 squared times 1, 2. That is 18 fifths times 1, 2, which you can write as 18 fifths, 36 fifths. So that's the vector that's parallel to u. That's y hat. Z is y minus y hat. That's the vector that's perpendicular to u. That's going to be 2 eighths minus 18 fifths, 36 fifths, or in other words, negative 8 fifths, 4 fifths. So here's what we end up with. Y equals y hat times z. 3 fourths equals y hat. This is y hat plus z. In other words, y, which is this red vector, is going to be y hat. Y hat is this long blue vector plus z. It's this perpendicular vector. It's perpendicular to y hat and perpendicular to u. U is this short vector over here. Y hat is parallel to u. An orthonormal set is an orthogonal set of unit vectors. An orthonormal basis is a basis of orthonormal vectors. For example, the set 1, 0, 0, 0, 1, 0, 0, 0, 1 is an orthonormal basis for R3. It's unit vectors, and they're orthogonal to each other. The set S equals 3, 1, 1, negative 1, 2, 1, negative 1, negative 4, 7 is an orthogonal basis for R3. We saw that earlier. Is it an orthonormal basis for R3? No, because the vectors are not unit vectors. Okay, to be an orthonormal basis, it has to consist of orthonormal vectors, vectors of length 1. Why do we care about this? Sometimes in matrix computations, it's helpful to use matrices with orthonormal columns. That is, the columns form an orthonormal set. For example, make the set 3, 1, 1, negative 1, 2, 1, negative 1, negative 4, 7 into an orthonormal basis for R3 by normalizing the vectors. That means making them of length 1. Well, recall that the unit vector in the direction of A is A divided by the length of A. So the orthonormal basis is going to be 3, 1, 1 divided by the length of 3, 1, 1. Negative 1, 2, 1 divided by its length. Negative 1, negative 4, 7 divided by its length. So in other words, the lengths are going to be root 11, root 6, and root 66. Maybe I should root 66. Get your kicks on root 66. So we've got, in other words, 3 over root 11, 1 over root 11, 1 over root 11, negative 1 over root 6, 2 over root 6, 1 over root 6, negative 1 over root 66, negative 4 over root 66, 7 over root 66. An M-bind matrix U has orthonormal columns if and only if U transpose U equals the identity matrix. Let's confirm this in the case of U. Well, you can confirm it. It takes a long time to plug in. You use Mathematica, and you end up with this, which wasn't much of a confirmation. This was frustrating. I calculated U transpose U, expecting it to come out I, and it doesn't come out as I. It just comes out as this nonsense. That doesn't look like the identity matrix. But it turns out that this second component is 0. This component is 0. This is 0. And this is 0. So we do get 1, 0, 0, 0, 1, 0, and 0, 0, 1. So it really does turn up to be the identity matrix. So again, M-bind matrix has orthonormal columns if and only if U transpose U is the identity. So I confirm this in the case of this matrix U. It works. Dandy. That's great. Let U be an m by n matrix with orthonormal columns, and let x and y be an Rn. Then the length of Ux is the length of x. Ux dot Uy is the same as x dot y. And Ux dot Uy equals 0 if and only if x dot y equals 0. That just follows from the second statement. Notice that the first and third properties imply that the linear transformation x to ux preserves length and orthogonality, which is important for certain computer algorithms. So that's a property of U, an m by n matrix with orthonormal columns. A square matrix U is an orthonormal matrix if U transpose equals U inverse. Now, by the above definition of orthonormal columns, this one we saw a moment ago, U transpose U equals the identity matrix. So by that definition, the square matrix U is an orthonormal matrix if U has orthonormal columns, since U transpose equals U inverse if and only if U transpose U is the identity. Just take this and multiply both sides by U inverse on the right, and you'll get U transpose equals U inverse. Some books call such a matrix U an orthogonal matrix, which is confusing because the columns are not merely orthogonal, but orthonormal. But whether the book uses it or not, this is our definition of an orthonormal matrix or an orthogonal matrix. A square matrix U is orthonormal or orthogonal if U transpose equals U inverse.